see that. Today we're going to talk about a special concept in green chemistry and how it can help achieve the state of the art. This concept is called biocatalysis. Stick around, you might learn a few things.
Biocatalysis is the use of protein enzymes and living organisms as catalysts in reactions. Just like the catalyst you are used to, a biocatalyst serves the same purpose and function. Your reactants come in, and they react after binding to the active sites, after which the products detach from the enzyme. A biocatalyst has a few advantages over traditional catalysts. With a biocatalyst, you can maximize the yield of a specific enantiomer you desire. This can reduce the amount of waste byproducts you produce. You can also target specific functional groups to undergo your reaction, which helps to reduce the use of protecting agents. This can also lead to easier separation of your products. Another advantage is the use of modern computational techniques to modify your enzyme for very specific properties. This can be a time-consuming process and requires deep knowledge of protein structures with respect to its function. Alternatively, you can do multiple random modifications on your enzymes until you achieve your desired properties. Biocatalysis is a fairly new concept, but it wasn't until the 19th century when a French chemist, Louis Pasteur, discovered there was actually yeast converting sugars into ethanol in alcoholic beverages. This was one of the first steps into realizing the potential of using enzymes as biocatalysts. Now that you have an idea of what biocatalysis is about, let me show you how it can be utilized in modern chemical industries. One of the most extensively used synthetic fibers today is polyester, a high molecular weight polymer. It is synthesized through ring opening polymerization or polycondensation reactions. Modern methods require high reaction temperatures, the use of metal catalyst, which can be toxic, and have very low selectivity. Turns out, the enzyme lipase can be used as a biocatalyst when synthesizing polyester. Lipase is a subclass of hydrolase whose role is to catalyze hydrolysis reactions. In the case of lipase, it hydrolyzes the ester links of lipids to produce glycerol and fatty acids. Now, how can an enzyme that is used to cleave molecules be used to condense them together?
Well, the lipase actually catalyzes ring opening polymerization. Specifically, cyclic esters such as caprolactone are precursor to the biodegradable polyester polycaprolactone. Here's a high-quality animation to help you visualize this reaction. So you start with your caprolactone molecule. The lipase comes in and it attacks this bond. This forms your reactive nucleophilic alkoxide, which can then attack this carbon. Forming another alkoxide. The bond joins here. This process repeats many times, which then forms your polycaprolactone. Here's one I prepared earlier.
So let's talk about this from a green chemistry perspective. The traditional method of synthesizing polycaprolactone usually requires toluene as a solvent. It is both toxic and highly flammable. The lipase-catalyzed reaction can use either water or supercritical carbon dioxide. which are both green solvents. The reaction temperature is usually between 25 to 70 degrees Celsius. Compare that to 125 degrees when using a metal catalyst. That's a little less energy required. Metal catalyst lacks selectivity, so your product exists as a racemic mixture requiring further separation. Lipase is both non-toxic and has great selectivity, giving you greater yield of your desired product while reducing the amount of byproduct and waste you produce.
And that is all the time we have. Hope you learned something new. And remember, clean and green keeps the world pristine.